In this video, we are going to solve a prepositional logic problem. The question is, prove the logical equivalence of P implies R and Q implies R equivalent to P or Q implies R. To prove this logical equivalence, we will use two methods. One is using truth table and second algebraic method. First, we determine the number of rows in the truth table, which is 2 raised to 3 equals 8, because there are only 3 variables P, Q and R. Each variable is a statement. If you remember, two or more variables make a compound statements. Since using English statements are difficult, we will use the variables for convenience. Now construct the table. So I pause here for a few seconds. The table headings are P, Q and R. Then P implies R. You can call this as 1. The next column is Q implies R. We call this as 2. The next column is 1 and 2, where 1 is P implies R and 2 is Q implies R. Then we have P or Q, and finally P or Q implies R. First enter truth values for column P, Q and R. The P column first 4 entries are true and last 4 are false. Enter the P column values first. The Q column first 2 are true and the next 2 are false, and it follow the same pattern. Enter values for Q column. The R column has first true value and then false, and it alternate between true and false. So enter all values for R. Enter values for P implies R column. The P implies R column uses implications. Therefore, if P column value is false or R column values are true, then the P implies R column value is true. Otherwise, it is false. Enter true when P is false or Q is true. Else enter false. Similarly, we need to evaluate for Q implies R column. When the Q is false or R column value is true, enter true for Q implies R column, otherwise enter false. First, we mark all the rows where Q is false and then mark all the rows where R is true. Now enter values in Q implies R column. Enter the truth value for column 1 and 2. Whenever column 1 is true and column 2 is also true, enter a true in the column 1 and 2, else enter a false. Mark all the columns where P implies R is true and Q implies R is true. Then enter true for column 1 and 2 in the same row. Like this, enter all the values. The next column is P or Q column, which can be evaluated using P column values or Q column values. If P column is true or Q column value is true, the P or Q column value is then true, else it is false. Enter the truth values for this column. Finally, the last column is P or Q implies R. So you need to evaluate this column based on the entries of P or Q column and R column. Now this is an implication, therefore we mark all the entries of P or Q column where it is false. Also we look for all the entries in R column where it is true and mark it. For these entries, you enter true for the P or Q implies R column. Now if we compare the values of column 1 and 2 and P or Q implies R column, both are same and implies that the logical equivalence is true. Hence it is proved. The logical equivalence can also be proved using prepositional identities, and this technique is called the algebraic method. It is a way of translating the logical equivalence into something simple so that we could prove the logical equivalence or disprove it. So the given equivalence is P implies R and Q implies R is equivalent to P or Q implies R. First, we simplify all the implications and change the equivalence to something simple by applying certain prepositional identities. For this, we need already established identities. If you want to learn about these identities, then I recommend you to watch my video about logical equivalences and know the topic well. So we use identity P implies Q equivalent to not P or Q. Our new equation is not P or R and not Q or R is equivalent to not of P or Q or R. This equivalence is simplified, but it is not what we need. It is not same on both sides, so we need to simplify it again. We can use another identity called the distributive law. By distributive law, Q and R or P is equivalent to Q or P and R or P. Applying distributive law to the left-hand compound preposition, we get not P and not Q or R, which is equivalent to not P or Q or R. Now simplify the right-hand side preposition because the equivalence is still not the same. Note that the implication and negation are of higher precedence operator, meaning they rank higher in the list of logical operators. So we must always simplify them first. So not P or Q becomes not P and not Q, and our equivalence becomes not P and not Q or R is equivalent to not P and not Q or R. Now the original equivalence is same on left hand side as well as right hand side. Therefore the logical equivalence is valid and hence proved.